Motional EMF, as well as any other type of induced EMF, can be described in terms of a concept called magnetic flux. Magnetic flux is analogous to electric flux, which deals with the electric field and the surface through which it passes. Magnetic flux is defined in a similar way by bringing together the magnetic field and the surface through which it passes. We can now explore how the motional EMF is related to the magnetic flux by examining the moving rod we use to derive the motional EMF, equal to the velocity times the field times the length, in a slightly different way. We will now examine how the changing area of the complete loop, that is the electrical circuit defined by the wires, the light bulb, and the bar, is related to the induced EMF. The rod has a length L, same as the width of the rectangular loop, and begins moving through the magnetic field at time t equals 0 seconds. In a time t0, it has moved to position x0, and finally to position x after a time t. We know from the previous section that the EMF of a rod of length L moving through a magnetic field B with speed v is equal to BLV. The speed v of the rod between the positions x0 and x is the distance traveled, x minus x0, divided by the elapsed time, or v equals x minus x0 divided by t minus t0. Substituting this expression for v gives BL times x minus x0 divided by t minus t0, which is equal to b times xl minus x0l divided by t minus t0. The term x0l is the area A0, and xl is the area A, so this equals b times a minus a0 divided by t minus t0. We can rearrange this so that the EMF equals BA minus BA0 divided by t minus t0. The term BA, the product of the field and the area, is defined as the magnetic flux, phi, so we can write phi minus phi 0 divided by t minus t0 equals delta phi divided by delta t. Therefore, the magnitude of the EMF is the change in magnetic flux divided by the change in time, or EMF equals delta phi divided by delta t. You will almost always see this equation written with a minus sign, namely EMF equals negative delta phi divided by delta t. The minus sign is introduced for the following reason. The direction of the current induced in the circuit is such that the magnetic force acts on the rod to oppose its motion, thereby tending to slow down the rod. The minus sign ensures that the polarity of the induced EMF sends the induced current in the proper direction so as to give rise to this opposing magnetic force. This issue of the polarity of the induced EMF will be discussed further in the next section. The advantage of writing the induced EMF with the minus sign is that this relation is far more general than our present discussion suggests. We will see that the form of the equation including the minus sign can be applied to all possible ways of generating induced EMFs. In our preceding discussion, the direction of the magnetic field B was perpendicular to the surface swept out by the moving rod. In general, however, B may not be perpendicular to the surface. For instance, consider the more general case. Here we have the surface area A with a direction perpendicular to the surface indicated by the normal to the surface. The magnetic field is now inclined at an angle phi with respect to this direction, rather than being parallel to it as in our previous discussion. In such a case, the flux is computed using only the component of the field perpendicular to the surface, or B cosine phi. The general expression for magnetic flux is then given by phi equals B times A times cosine phi. The units for flux are T times m squared, which is equal to the Weber, given by the symbol W. From this general equation for the magnetic flux, we can see how the different parameters can change its value. For instance, changing the field strength, which is illustrated by changing the number of field lines, everything else being the same, the area A and the angle phi, changes the magnetic flux. Keeping the field and angle unchanged, but changing the area, changes the flux. Finally, keeping the field and area unchanged, but changing the angle, also changes the flux. We see here, graphically, that the flux is a maximum when the field is perpendicular to the surface, or when the angle between the field and the surface normal, phi, equals 0. The flux is a minimum, 0, when phi equals 90 degrees. In summary, the general equation for the magnetic flux is given by phi equals BA cosine phi, where phi is the angle between the field and the surface normal. The units for magnetic flux are Tesla times meter squared, which is equal to the Weber, and given the symbol W. Finally, the magnitude of the induced EMF in a closed loop is given by the time rate of change of magnetic flux, or EMF equals delta phi divided by delta t. As you will encounter in future sections, this equation will include a minus sign so that it can apply more generally to all possible ways of generating induced EMFs.